Welcome to Microwave and Electromagnetics lecture series. I, Professor Hitesh Dolakia, is going to explain you Smith chart example for VSWR, reflection coefficient and input impedance calculation in this video. So to explain you this example, here we have a transmission line you can see. With this transmission line, load impedance is ZL, that is 100 plus J40 ohm. Characteristic impedance of this transmission line is 50 ohm, and this transmission line is operated at 3 gigahertz of frequency. Here length of this transmission line, that is 2.5 centimeter, and here we are deal with to have input impedance in between these two terminal. So for this transmission line, we are deal with to identify VSWR, reflection coefficient and input impedance. So my dear friends, you see here we have Smith chart, and in this Smith chart we will be identifying these three parameters step by step. So whenever you want to calculate VSWR or reflection coefficient based on load impedance, then first step is to translate given load impedance in terms of normalized load impedance. So first of all, we should be translating this load impedance into normalized load impedance, and normalized load impedance is this load impedance divided by characteristic impedance. So you see, we will be finding normalized load impedance, that is ZL divided by Z0. ZL is 100 plus J40, Z0 is 50. So 100 divided by 50, that is 2, which is real component, and imaginary component is plus J40 divided by 50, so that is plus J0.8. So this point that we are deal with to place in this Smith chart first. Now whenever you want to plot this point ZL, normalized impedance ZL in Smith chart, one should know some basics of Smith chart. See, these are the circles, these are the complete circles, that is real circles, and these half circles are imaginary circles. Now upper half imaginary circles are positive imaginary circles, and lower half imaginary circles are negative imaginary circles. Now our agenda is to have ZL, which is having real 2. So you see real 2 circle, that is this one, and plus J 0.8 that we need to have. So 0.8 plus J, that is this semicircle you see, which is plus J 0.8. So that is intersecting at this instant you see. So this is our ZL, which is 2 plus J 0.8. Now once you point out this point ZL is equals to something on Smith chart, next step is to identify VSWR circle. Now VSWR circle that we can have by a center, which is this, and with this radius of ZL we can have a circle which will be VSWR circle. So you see I am drawing this VSWR circle over here, that is having center this, and radius will be this ZL point. Now once you have this VSWR circle, from here you can stretch a straight line on this scale, and if you see carefully on this scale, then this first scale that identifies VSWR value, and this third line that identifies reflection coefficient. So here if you observe this, so that identifies VSWR, and that is approximately 2.4, and if you see this reflection coefficient, then that is approximately 0.4. So now we have calculated VSWR, that is 2.4, and reflection coefficient, that is 0.4. Now our next question is to identify input impedance. Now my dear friends, you see input impedance is measured from this two terminal. So here when you want to measure input impedance with respect to this load and transmission line, then from the load you'll have to move towards the generator. So when you want to measure input impedance from the load, you will have to move towards the generator. So towards the generator, we are dealt with to move by length is equals to 2.5 centimeter. Now, dear students, you will have to understand this. See, on Smith chart, we cannot have length movement in terms of centimeter or meter. We can only move length in terms of lambda. So now we will have to translate this length in terms of lambda. So first we will have to stretch a straight line from the center to the load, right? So this is the line which we are stretching. So from here we will have to move by length L in terms of lambda towards the generator, means in clockwise direction. So now we will translate this length in terms of lambda. So lambda is velocity c divided by frequency f. So that is 10 centimeter. Here c is 3 into 10 to the power 10 centimeter per second, and f is 3 gigahertz. So that is 3 into 10 to the power 9. So our wavelength is 10 centimeter. Now you see length is given, that is 2.5 centimeter. So in terms of wavelength, length is 0.25 lambda. So now our agenda is to move point from this point by 0.25 lambda in clockwise direction. Now whenever you have wavelength in terms of 0.25 lambda, then remember this thing. You see this complete VSWR circle is having length of 0.5 lambda. So half circle of this VSWR is having length 0.25 lambda. So here if you stretch this straight line like this, then obviously this half of the circle will be having moment of 0.25 lambda. Right, so now we will be pointing a point which is having moment of 0.25 lambda in clockwise direction. So that will be exactly opposite point to this line, right? Now here we need to see at which point this line is intersecting to VSWR circle. So that is intersecting somewhere over here, you see. Now over here if you observe, this point is having real value, that is somewhere in between 0.4 and 0.5, and imaginary circles, that is negative over here, and that is bit lower than 0.2 that you can observe, right? So real is 0.4 and something, and imaginary is negative 1 point something, right? So this is the point, and that point is exactly 0.43 minus j 0.17. Minus is because of this imaginary circles are negative. Now this is what normalized input impedance that we have. So to have exact value, all we need to do is we need to multiply Z0 with this normalized input impedance to have exact value of input impedance. So if you multiply 50 with this, then 0.43 into 50, that is 21.5, minus j 0.17 into 50, that is 8.5. So this is our input impedance for this transmission line by using Smith chart. I hope now you have understood how we can identify input impedance based on Smith chart as per the explanation which I have given over here. Thank you so much for watching this video, and you can download all this material from my application Engineering Funda, where I have placed PDF of all the questions which I have solved regarding Smith chart. That will be definitely going to help you to understand Smith chart examples. And there are many other examples related Smith chart that I have placed it in my playlist of microwave engineering and electromagnetics. You can go through it. And your suggestions are always welcome. Thank you so much.